Hey guys, welcome to the next lecture. Today I'll be focusing on two concepts here. Number one, continuity of inverse functions, as you can see on the screen. And number two, the intermediate value theorem. So when we talk of inverse function, what essentially is an inverse function? If f is any function, the inverse of f graphically is just a reflection of f on the line y equals to x. Therefore, there's a generalized theorem which says that if f is a one-to-one function that is continuous at each point in its domain, then f inverse is continuous at each point of its domain as well. And well, what is the domain for f inverse? It's the range of f. So therefore, that is f inverse is continuous at each point of range of f. Right? Now, why it is happening like that? The intuition behind this generalization is that since the graph of any one-to-one function is just the reflection on the line y equals to x, so in case there are no breaks for f, there won't be any break for f inverse as well. Since the graph of a one-to-one function f and its inverse, f inverse, are just reflection of one another about the line y equals to x, so what can you interpret out of it geometrically? If there are no breaks, no holes in f, automatically the reflection will also not have any hole or break. So let's see if we've understood the concept or not. For that, I have a question for you. Fx is equal to x cubed plus x. Does f have an inverse? If yes, is f inverse continuous in minus infinity to plus infinity, that is R? Let's see how we can go about this question. We can analyze this function. So this function x cubed plus x, if you differentiate it, it's a polynomial, so you can differentiate it. You will get 3x squared plus 1. Well, x squared, no matter whether x is positive or negative, will always be positive. So that means this is strictly greater than 0. And the moment f dash is strictly greater than 0, that implies f is strictly increasing. And a strictly increasing function is always one-to-one, remember? Because every new value of x will provide you a new value of the function at that point, right? So it's a one-to-one function. In case this function is one-to-one, what can we say? Using the generalization or theorem that we have, if f is one-to-one and it's continuous, polynomials are continuous, we've already dealt with that. So it's continuous, it's one-to-one at each point in the domain. For all x, this is strictly increasing. So it's one-to-one for all x belonging to R. And therefore, that implies that definitely f inverse exists for all x in R. So when I was trying to explain give you the intuition of this theorem, what did I say? That f inverse would be continuous. Is f inverse continuous is the next question. So f inverse would be continuous in case f is continuous, f is one-to-one continuous function, then f inverse will be continuous. F inverse does exist here. That implies now, because f is continuous in its domain, and the domain of f is minus infinity to infinity, that tells you that f inverse is continuous. And where will f inverse be continuous? F inverse will be continuous in the range of f. In the range of f. And what is range of f? Can you tell me that? Quick revision for you. I think you should pause and figure out what is the range for f. F is x cubed plus x. So range of f, which is x cubed plus x. Since f is increasing, Since f is increasing, therefore that implies the range of f, it's a continuous and increasing function. Range of f will be minus infinity to infinity, everything, because the input domain is minus infinity to infinity. And this is a continuous and increasing function. So hence the range will be minus infinity to infinity. Okay. So yes, this is continuous, and where? In entire R. Next, I want to talk to you guys regarding the intermediate value theorem. A very, very important part of continuity is intermediate value theorem. Continuity as a concept gets life when you talk about intermediate value theorem, because there are so many things that, so many consequences that can come out of continuity when you start thinking in terms of intermediate value theorem. Yes. As you can see, the word mentioned here, intermediate. So the intermediate value theorem talks about the intermediate values. Intermediate values mean values which are lying in between something. Okay. So intermediate value theorem is just telling you a fact about a continuous function. Suppose you have a continuous function in certain domain and it's going like this. So this is point A, and say this is point B. This is point A, this is point B, and I can see that this graph is continuous. This is y equals to fx. This is clearly fx is continuous on the interval closed AB. It's definitely continuous at the endpoints as well. So hence it's continuous in closed interval AB. If you pick any value between FA and FB, so this point that you will get here is FA. So this point is A comma FA. This point that you will generate here is the value at B. So this point is B comma FB, right? So if you have any value in between FA and FB, that has to be getting generated by some intermediate value between A and B. So an intermediate value between FA and FB must be getting generated by an intermediate value between A and B, because this is a continuous function. It cannot come from anywhere else. It has to come from the domain AB. More formally, if you take a situation where we draw a horizontal line K, where K is a value between FA and FB. So I am drawing this line y equals to K. It will cut the graph somewhere, right? It will cut the graph somewhere. It will cross the graph somewhere. It will cross y equals to fx at least once, right? It will cross at least once. It will cross it because it's coming from in between FA and FB. So it will, when it's a horizontal line, so it has to cross the graph at least at one point. That point is definitely between A and B. That's the whole idea about intermediate value theorem. Let's make it look a little more practical. So let's take a polynomial. Polynomials are always continuous, right? So it's a continuous function, x to the power 5 minus x plus 3. So P1, when you put the value of x as 1, you will get 1 minus 1 plus 3. So it's 3. P2 is equal to 2 to the power 4 minus 2 plus 3. That's going to be 33. Okay. So what is intermediate value theorem in terms of this polynomial? So in terms of this polynomial, if you take K, which is between 3 and 33, intermediate value theorem is just saying that there has to be some point in between 1 and 2, which is giving you this value K, because this is a continuous graph. all the values in between 3 and 33 must be getting generated by some values which are between 1 and 2. That's what intermediate value theorem is telling you. In other words, x to the power 5 minus x minus plus 3 equals to k has at least one solution. Has at least one solution in between 1 and 2. Because that value must be getting generated between 1 and 2 only, because the value at 1 is 3 and the value at 2 is 33, where k is a value between 3 and 33. I think now we are in a situation to formally state this theorem. So this theorem is basically telling you if f is continuous, if f is continuous on a closed interval and k is any number between fa and fb, including both fa and fb, then there is at least one number x belonging to closed AB such that fx is equal to k. Exactly what we have discussed before and seen through the example. What is the best part of intermediate value theorem is that you just require continuity as far as the prerequisite for the function is concerned. It's just continuity of the function which is required. But yes, that's important. The function must be continuous, then only you can talk about intermediate value theorem. The second important thing about intermediate value theorem is the consequence of intermediate value theorem in approximating roots for functions, continuous functions. Intermediate value theorem, it really helps you in figuring out whether root of a function would exist, in certain interval or not. For example, if say you have the function x cube minus x minus 1 equals to 0. When we talk about the root, we talk about equal to 0. That's what root means, right? Cutting the x-axis somewhere. So whether x cube minus x minus 1 will cut the x-axis or not, or where exactly would it be, cutting the x-axis, that's something that you can figure out using intermediate value theorem. And in a very simple manner. Let's see how. Let's consider x equal to 1. So, or x equal to 0. Let's start with 0. Yes, you have to do a hit and trial here. Put x equal to 0. That would give you that x cube that will become 0 cube minus 0 minus 1. That gives you minus 1, right? So consider the polynomial fx equals to x cube minus x minus 1. We need to know whether this function can take the value 0 and around where will it take the value 0 if it is taking the value 0. If you are getting fx equal to 0 anywhere. So where approximately you will get it. Suppose I put x equal to 0, I'm getting minus 1. If I put x equal to 1, I'm going to get 1 minus 1 minus 1, which again is minus 1. Okay. If I put x equal to 2, I'm going to get 2 cube minus 2 minus 1, which gives you 8 minus 3, that is 5. So what essentially is happening between 1 and 2? Between 1 and 2, there's a sudden change occurring. So at 1, the value of the function is less than 0. At 2, it's more than 0. So f1 is less than 0. f2 is greater than 0. Logically, if you think of the graph of this function, I'm not graphing it completely, but I'm just trying to tell you here what is happening. When x is 1, the value of the function is negative. Okay, the value of the function is negative. So the graph, since it's a polynomial, it's continuous, it is continuously It must be continuously raising itself and reaching a positive value at 2, right? In between, logically think about it. In between, it must be cutting the x-axis somewhere, right? It must be cutting the x-axis once at least, right? It must be at least once cutting the x-axis and moving up, right? So, what is the consequence of intermediate value theorem? So, you take this as your FA, this as your FB. A and B, A is 1, B is 2. What you realize is that 0 is a value which lies between F1 and F2. This value must be getting generated by some number which is between 1 and 2. So 0 is your K. 0 is that K. K is any number between FA and FB. Then there is at least one number x in AB such that fx equals to K. So that means there exists at least one x between AB. You can write down closed 1 to 2, but since you know the value at 1 is not 0 and value at 2 is not 0, you might as well write down open. So whether you write down x belongs to open 1 to 2, it won't be wrong. Whether you write down it is between closed 1 to 2, it won't be wrong. In the theorem, you must have noticed that we have written closed AB. Because yes, maybe FA itself is equal to K or FB itself is equal to K. That's possible, right? But in case you know that FA, FB is not equal to K, then you can even write down open. That's what I've done here. I've written open interval 1 to 2 because I know F1 is not equal to 0, F2 is not equal to 0. That's the reason. Okay. So there is some x, at least one x between 1 and 2, such that fx is equal to k. K is 0. So this is a very important consequence of intermediate value theorem. More formally, let's just write it down. If f is continuous, on closed interval AB, and if FA and FB are non-zero and have opposite signs, one is greater than 0, one is smaller, lower than 0, then there is at least one solution of the equation fx equals to 0. That means there is at least one root in open AB. Because again, I've specified that FA and FB are non-zero here. Let's use this concept in another question. So you have to tell me, suppose that a function f is continuous everywhere and f of minus 2 is 3, f of minus 1 is minus 1, f of 0 is minus 4, f of 1 is 1 and f of 2 is 5. Does IVT, the intermediate value theorem, guarantees that f has a root on the following intervals? Minus 2 to minus 1, minus 1 to 0, minus 1 to 1, 0 to 2. Let's look at the first one. Minus 2 to minus 1. So consider f of minus 2. F of minus 2 is 3. And f of minus 1 is minus 1. So yes, this is greater than 0 and this is less than 0. So therefore, we do have fx equals to 0 for some x which is between this interval, which belongs to minus 2 to minus 1, right? The next one is b, which is -1 to 0. So f of -1 is -1, which is less than 0. F of 0 is -4, which is also less than 0. So graphically also, if you will see, so it is -1 and then it is -4. Okay, so it's just going down. It is not cutting the x-axis definitely in between. So this is not, you're not getting a root here. Okay, the answer that IVT guarantees, no. Here it will not. Number C is -1 to 1. -1 to 1. So f of -1 is equal to -1, which is less than 0. F of 1, I got to check what it is. It is 1, which is greater than 0. So the answer here is yes. IVT does guarantee a root here. And number 4 is 0, 2. So f of 0 is -4, which is less than 0. And f of 2, I got to see what it is. F of 2 is 5, which is greater than 0. So that means since the opposite signs are there, so it will be cutting the x-axis somewhere. So yes, we do have a root here. So if I had to convert it to an MCQ, I would have actually asked you which one does not have a root in, which in which interval f doesn't have a root. Okay, that would have been my question. Then B would have been the correct answer. Which interval cannot have a root of f? The answer would have been B, which is -1 to 0. That would have been the correct answer. Thank you.